torque causes something to spin, okay? Causes rotation. Rotation. Oops, I got an extra T in there. Rotation. Sorry. Okay. Torque causes rotation. Okay. Now, not only does it cause rotation, it causes rotational acceleration. All right. Well, what is rotational acceleration? How can we quantify that? Okay. What we do is we say if A is F over M, then the angular acceleration, which is a good descriptor of the angular or the rotational acceleration, that's our angular acceleration. That's going to be equal to the rotational force over the rotational mass. Okay. Now that's that might sound like, well, Professor Hale, that sounds really cute to just rename these things. But by our definitions of moment of inertia, or the rotational mass, and by our definitions of torque, this is actually an accurate description. By applying force to every little bit of mass over a rigid object, we will get this equation come out. And what's beautiful is it does have the same form. So by knowing how to use Newton's second law in this form very clearly, we can just now apply it to this law very clearly. Okay. So we need to embellish this just like we did with this one and make sure we can understand it clearly. First of all, okay, what I care about is alpha is from the net torque, okay, over the moment of inertia of the object. So if there are multiple forces applied to this object in multiple positions at multiple angles, we're going to have a torque from each one, and the acceleration of the object depends on the net torque. So we have to add them all up. Okay, now what if one torque is causing it to spin clockwise and another torque is causing it to spin counterclockwise, or it would if it was alone? Then we need to care about those directions. So this is dependent on both size and direction, and this angular acceleration has a direction too, clockwise versus counterclockwise. It's a little bit easier than this because this could be x, y, and z. This one is either just clockwise or counterclockwise. And so we establish kind of a direction to be positive and negative. Now, technically, you can pick whichever direction you want to be positive or negative, but there is a convention that is used generally. That is, counterclockwise, CCW, is considered positive. Okay? So if something is moving counterclockwise, we say it's got a positive rotation. If something is moving clockwise, it's got a negative rotation. If something is speeding up in this counterclockwise direction, it's got a positive acceleration. If the torque would cause it to rotate this way, it'd be a positive torque. So this vector sign is there to remind us that direction matters. So, for example, if I have a disk here and I apply a force on it in a variety of different ways. So I apply one force here, F1, and I apply another force here, called F2, and I apply another force here, F3, and I can apply another force somewhere else. Well, this force would cause this thing about an axis to its center, would cause it to rotate that way. So this alone would cause it to rotate in the counterclockwise direction. So this would cause a positive torque. This one too would cause it to rotate counterclockwise. So it would be a positive torque. This one would cause it by itself to rotate clockwise, which means this would be a negative torque. The acceleration depends on how big these are. Just from the size of these vectors, the angles I've drawn them at, these two would dominate over this one, so there would be a net counterclockwise acceleration, so this would be positive. So generally we use this numerically, but we do put in pluses and minuses when trying to consider the torque.